Hey everyone, this is a little mini lecture on using the SignalTemporalLogic Julia package that I put together that we use throughout the textbook and throughout the project assignments. And so I just want to give you a little quick introduction on how to install it and how to use it in its basic format. So first things first is how to install the package. So if you open up a Julia terminal, you can install the package via pkg.add, the SignalTemporalLogic package. And then to use it, you can just say using SignalTemporalLogic. For the project assignments, we do this for you so you have access to the code already. Next, I want to talk about how to define a specification in the package. So as we've seen in class today, let's define the following specification, which says that eventually, which is this lozenge or this triangle, the state will be greater than 0, just as we saw in lecture. So first in Julia, we can say using SignalTemporalLogic. Then we can define a trajectory, which is just some set of states or a signal here, which we plot on the right. Then just for your own knowledge, to get the tau symbol in Julia, you can do \tau and then hit tab. Next, we will define the formula. So this is the SignalTemporalLogic package in action. Here we use the @formula macro in Julia, and we can then type in Unicode that follows the formula itself pretty closely to the math. So what this is saying is eventually the state S will be greater than 0, and we use this anonymous function notation as that mu, as we saw in class. And again, just so you're aware, to get the psi here, we can do /psi, and then to get the lozenge, we can do /lozenge. And then next, we can just use that specification and we can evaluate the trajectory. So we can pass in the trajectory to that specification, and this will evaluate whether or not that specific trajectory, that set of signals, evaluated to true or false. And in this case, because we can see that all of the points on this trajectory were below 0, this evaluated to false. If instead we change the trajectory to the one we saw in class, where there are some that are above that threshold 0, we can see the specification evaluates to true. Next, which we talked about in class, I want to go over how we can define and use robustness in this package. So say we have that same trajectory from the previous slide, and we can just use the rho symbol in Julia to define the robustness given the trajectory and given the specification. And this will give you the value of, say, 3. And to get rho, you do /rho. So we have another formula, which is always above 0. We can use /square to get that. And we see that the robustness is -4. And just as we went over in class, this has to do with the min and max values defined for the eventually and for the always operators on how robustness is defined for these. And so we can see what values are given for those. So for the maximum, we can see is in blue here for the eventually, and the minimum is in green here for always. Just to dive a little further, let's see how we define the eventually operator in Julia. So it's actually defined, spelled out, instead of just as the lozenge character that we see here. So eventually is defined as a formula type, which itself has a formula and some interval. And so what this really says is eventually actually is just defined as eventually between some time step A and B, the formula, this inner formula psi, holds true. What this really means is that it's true until between A and B, psi holds. So you can actually use some previously defined functionality of STL to define some new operators. In other words, this really just says that there exists some time in that window between A and B where psi at time t holds true. And so in Julia, we can define the function operator for eventually, which given some eventually formula and some set of signals x, we can just say, any of those sub-formulas psi for some interval evaluate to true, then we return true. We can also define robustness and smooth robustness. So as examples from the textbook and from lecture, the robustness of eventually is defined as the max over that time step range of the robustness of that inner formula. And in Julia, this is just the maximum of the robustness, which is a recursive call based on the type of this formula here. We can also define the smooth max, which is the same thing, but now we have this smooth max function, which we define as shown in class here as just if the weight is 0, then we just return the maximum. So this was, if we want to just go back to the normal maximum, we set a weight or a smoothness value of 0. Otherwise, we use this formula here. And one of the nice things about this is you can see if we just used the maximum and we try to take, say, a gradient of the robustness, then the maximum doesn't really play well with gradients as shown in lecture. And so if we have a weight value anything other than 0, then all of the functions that we're actually running within Julia are, say, sum, some multiplicative or multiplier, exponentiation, division, and so forth. And so these are really simple operations. And what this means, though, which is really nice, is that we can use Julia's built-in auto-differentiation packages right out of the box. So to give you an example, if you use some signal temporal logic, we also import, say, gradient from one of the differentiation packages in Julia. Here is forward diff, which we provide to you in projects 1 and 2. We have that same signal, that same trajectory, and here's our formula. Then we can just say gradient of the robustness given the formula with respect to tau. So we just pass that in. And this gives us that gradient that we saw in lecture, where it's 0 everywhere except for right when the signal changes. But again, that may not be super useful when you're, say, using robustness as a measure within optimization for its objective. So we can use the smooth robustness, which is tau tilde, which you can get by writing /rho, actually not tau tilde, rho tilde, /rho, /tilde, and tab for each of those, and it'll create this character here. And then we can see that the robustness gradient is now smooth, and we have a default weight of 1 set here. So we can see that this does not match directly to the maximum like we saw before, but we do see that the values are indicative of where that maximum would be, which, say, is right here at 0.96 compared to the 1 here. One thing you might note is that in the textbooks and the projects, you can use aliases for rho and rho tilde, so you don't have to keep typing out /rho and /rho tilde. We just call those robustness and smooth robustness, where the smooth robustness takes in a weight parameter. Under the hood, it's just an alias for rho and rho tilde. We also provide wrappers around that at formula in the textbook. So we have an LTL specification, which just specifies a formula. And to evaluate it, we pull out the states within some trajectory that you see throughout the textbook, and we evaluate that formula as we did before. For signal temporal logic, which includes a time interval I, we do the same thing where we wrap that and we just do this for some time interval I. Now, to show you some examples of how this applies to some of the problems that you'll do and you'll get some experience within the projects and within the textbook. For the grid world, as we saw before, one of the goals is to avoid obstacles at any time. So we have some predicate f that takes in a state at time t and saying state at time t contains an obstacle. So this is something we'd want to avoid. We also have another predicate g that says we reached the goal at time step t, and we have another predicate c that says that we reached the checkpoint at time step t. And so our full formula here would be, first of all, we eventually reach the goal, so that's what the lozenge here says, and we reach the checkpoint before the goal, so we say we don't reach the goal until the checkpoint, that's what this says here, and we always avoid obstacles. And what's nice is we can take this math and translate it directly into the signal temporal logic package by first defining what those predicates are, which are, we have some state for the obstacle, state for the goal, and state for the checkpoint, here defined just as one of the XY cells within this 10 by 10 grid world, and then the LTL specification, which is just a wrapper around the formula from STL, or signal temporal logic package. We can just write lozenge G wedge or slash wedge. This is slash SCR uppercase U or script U, and then negate G and then pass in C, or the box, which is the slash square, negate F. So this maps directly to the math, which is one of the reasons we love Julia. Next, I'll just show you some quick examples that Sydney went over in class. So for the continuum world problem, we want to reach the goal without hitting an obstacle, which we can do so in the Julia code like this, where we have some radius for what we mean by reaching a goal and hitting an obstacle, which is just a 0.5. We have the values, the centers of those circles for the goal and the obstacle, and then the formula maps nicely to the math. Next, we can talk about inverted pendulum, very similar, where we have the property that we want to keep the pendulum balanced, which is just saying the absolute value of our angle is less than or equal to pi over 4, so it stays in this green region. And in the code, it's very similar, or it's very simple, excuse me, where we just define some mu function here, which is just an anonymous function that says the absolute value of the first element of the state, which the state is two elements, both the angle and the angular momentum, or excuse me, angular velocity, which is less than or equal to pi over 4. In Julia, you can do /LE for less than or equal to and /pi for pi, and then the formula maps nicely to the math. And then lastly, for the collision avoidance problem says that we ensure at least 50 meters of relative altitude between the last time step here at 40 and 41 seconds. So here we can actually use a time interval between 40 and 41. And so the idea is we are always greater than an absolute relative altitude of 50 meters between time steps 40 and 41, and we can see how that's defined in the code. For more resources, you can see the signal temporal logic package itself, and you can look at the code, which is very simple. I showed you some examples of the inner workings here. And you can also look at the repository for the source of these slides here, where I made these slides in a combination of Beamer or LaTeX and Julia, and feel free to ask any questions you have on Ed. Thank you.